Warning, the video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is yet another video, third video in fact, in a series on the limit laws for differential calculus. In this video, we're going to prove the direct substitution property, at least for polynomials and rational functions. We'll only prove it for one of those. But this direct substitution property is actually broken into two separate theorems. One you get introduced to here, and again, like I said, it's only for polynomials and rationals, and then another one that you get introduced to later on. But for right now, let's focus on the one at hand. Before we begin, remember, and I keep reiterating this because I want all my students to be awesome with this, limit as x goes to a of f of x and the limit as x goes to a of g of x, you can use limit laws on those functions as long as those limits exist and are finite. That's incredibly important. So let's introduce ourselves to the direct substitution property. And again, this is for polynomials and rationals. If f is a polynomial or a rational function, and a is in the domain of your function f, then the limit as x goes to a of f of x is equal to f of a. This is sort of what we ran into in the last video, if you watched my last video. At the end of the last video, we had mentioned that we could have just evaluated this limit by plugging 5 in. Now, that is part of a more advanced direct substitution property. You cannot use that property until you've seen the theorem and seen the proof. So for now, we'll see this theorem for polynomials, and it actually does also go for rational functions as well. I don't have that written that way here, but this is also for rational functions. So as with any proof, you get to assume the antecedent, the if part. You get to assume that f is a polynomial. Don't assume it's rational. We're just not going to deal with that one. And we're also going to assume that a is in the domain of the function f. I shorthanded the language there. Suppose f is a polynomial and f at a exists. That means the same thing as a is in the domain of f. Well, since f is a polynomial, I know that I can write it in decreasing power order, and the exponents on all the variable terms, at least on all the variables, are going to be natural numbers. Assuming that f has degree n, f of x is some constant times x to the n, but then there could be another term because it's a polynomial, it could go on forever. So I'm going to go ahead and add another term here. That next term in line is just a different constant. I'm labeling all my constants with c sub something. C sub n minus 1 stands for the constant coefficient for the n minus first power of x. C sub n just means that's the constant coefficient for the nth power of x. Continuing the pattern, this would be c sub n minus 2, which is attached to the x to the n minus 2 power. And that pattern continues all the way down. So I'll just say plus dot dot dot. The ellipsis just means that the pattern we've created continues down forever until you get down to, let's say, c sub 2 x squared plus c sub 1 x to the first. I'll even write the 1 up there, plus c sub 0 x to the 0th. I could write x to the 0th if I want to, but x to the 0th is 1, so there's no point for that. That is a very general polynomial function. So far all I've assumed is f is a polynomial, and guess what? That's what f looks like. All polynomials pretty much can be written that way. Now what we want to prove is that the limit as x approaches a of f of x is equal to f at a. Let's see what happens. The limit as x approaches a of f of x, well, that's equal to the limit as x approaches a of all of this messiness. And yet we can break those apart using the limit laws. Again, when you use a limit law, you're not 100% sure if it's viable for you, so I'm going to put a question mark there. But I'm going to break this apart using the sum and difference limit law. And you can see I've almost run out of space here. I'm going to continue over here. All right, so this is how it would break apart if we're allowed to break that apart. Next thing I'm going to do is I'm going to go ahead and factor all the constants out of each of these limits. Remember, there is a constant product limit law, and so we're allowed to factor constant products off of those. So let's go ahead and do that. Again, I'll write a question mark there because I'm not 100% sure if I'm allowed to do this. And again, we need some more room here. Now, when I get to this final one, this guy right here, limit as x approaches a of c naught, that is just the limit of a constant limit law, which tells us since that does not have an x on there, the limit as x gets really close to a of a constant is just the constant. So I can at least rewrite that as c naught without a limit on it. And then finally, I get to use the limit of a power function limit law. So let me go ahead and again, just say, I don't know if this is going to equal to this. Let's see what happens. This is c sub n, a to the nth, plus c sub n minus 1, and so on and so forth down the line. You get down to there and you say to yourself, well, what the heck does that mean? Well, if you notice, that's the same thing that f would have turned into had we plugged a in. Remember, f of x is this ugliness up here. And had we just plugged a in, all of these values that have x's in them would have turned into a's, which is exactly what we have down here. So this is actually f at a, and I happen to know f of a exists because the function is defined at a. A is in the domain of f. And so these equalities with the question marks actually are equalities because it ends up being a finite number. It exists because f of a exists. So there we go. We've proven that the limit as x approaches a of f of x is equal to f of a if f is a polynomial. QED, quod erat demonstratum. So it has been demonstrated. And again, a similar proof holds for rational functions. Notice the level of detail that you use with proofs. You do not take an example, you keep everything as general as possible when you're doing proofs. So let's go ahead and use direct substitution property, or see if we can use the direct substitution property here. So this is not a polynomial, I totally get it. However, the other half of that theorem would be a proof that it works for rational functions as well, as long as, again, a is in the domain of the rational function. In other words, as long as we can plug in 0, we're allowed to plug in 0 if it's a polynomial or a rational function, which this is definitely a rational function. So let's see if I could just plug 0 in. Since x is definitely within the domain of this rational function, you can easily see, you've gone through algebra, I don't have to explain it as to why. That means that the limit as x goes to 0 of that function will just be f evaluated at 0. Plugging in 0 for all those values of x, you get 6 over 4 or 3/2. Now, you better believe that's more advantageous to use than step-by-step limit law justification. Luckily, you are now allowed to use this direct substitution property if you're handed a polynomial or a rational function. We didn't prove it for rational functions, I totally get it, but actually the proof for rational functions is incredibly similar to the proof for polynomial functions. All right, that actually does it for this video. So in the next video, we're going to go ahead and do something that's very, very, very important for us as we move forward through calculus, which is algebra. I'll see you there.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. listen close. Don't talk too much, that isn't cold. Sure, you may really hurt inside. It doesn't justify you to speak too loud and cry.